So now that we've kind of focused our attention on differential equations and using antiderivatives and things like that, we have to talk about undoing some of our more complicated derivative rules. So the most common rule that we're going to have to undo of the more complicated ones is the chain rule. And that requires a process or a technique known as integration by substitution, or you'll sometimes hear this called U substitution, which will make sense when we actually go through and talk about doing this. So a brief little thought experiment here to kind of illustrate why this is an issue. So here, if I want the indefinite integral of x to the fourth, that's saying what's the antiderivative of x to the fourth, which I know is 1/5 x to the fifth plus c. So then when I look at something like the antiderivative of 2x plus 3, all raised to the fourth, my initial reaction is, well, let's say it's 1/5 2x plus 3 to the fifth plus c, and say that's it. But then I can check these. So if I were to check and take the derivative of 1/5 x to the fifth plus c, I get 5 cancels the 1/5. I have x to the fourth plus 0. So that's okay. Whereas if I do this and check this one, 5 comes down, cancels the 1/5. I've got 2x plus 3 to the fourth. But then derivative of the inside times 2 plus 0. No, that's not going to work. And that's because of the chain rule. So we need a way of undoing the chain rule. And so that's where we get this process called integration by substitution, or U substitution. And the general idea behind this is, instead of trying to undo the entire derivative at once, we're going to undo the outside first and then undo the inside. Now, all of this should be taken with a grain of salt in terms of me saying solve for dx and substitute for dx. It's a manipulative way of describing what we're doing, but it's not a mathematically accurate description, but it gets the process down. The understanding of what mathematically is happening comes once you actually get more used to the process, and I know that feels a little backwards. So the first thing is saying, let's let u equal whatever the inside is. This does involve some trial and error, so you may try it and realize, oh, that doesn't work, and I have to start over. Is that frustrating? Yes. But is that part of the learning experience for this? Yes, as well. So here, it looks like 2x plus 3 is the inside part. So let's say u equals 2x plus 3. Well, then I want to find du dx. So the derivative of u with respect to x is going to equal 2. And since this is, I can think of this like a separable differential equation, I'm going to solve for dx. Although I should really say solve is in quotes here, because I'm not actually solving for dx. Oops, not to be 1/2 du. Because I can multiply both sides by dx, and then multiply both sides by 1/2 to get dx by itself. And then I can substitute these into my original integrand. So the 2x plus 3, so, oops, sorry about that. The 2x plus 3 can be replaced with u, and the dx can be replaced with 1/2 du. And what I'm looking for here is that there are no more x's left. If there are any x's left, it's a bad substitution. I have to start over and try to have u be equal to something else, or it means chain rule is not really involved. I can simplify this a little bit. 1/2 is a constant multiple, so I can pull that all the way out. And that's a much easier integral for me to figure out now. So I can evaluate that integral. So the 1/2 is a constant multiple. I just hold on to it. Antiderivative of u to the fourth would be 1/5 u to the fifth plus c. And then I was asked about this in terms of x, so I need to replace the u with what I said it was. So 1/2 times 1/5, parentheses 2x plus 3 to the fifth plus c. And now if I check this, the 5 comes down, cancels the 1/5. I have 2x plus 3 to the 4th. But then I have a 2 from the chain rule, which cancels the 1/2. And that works. So this is my antiderivative. So we undid the inside and the outside, but in separate places, so that we weren't trying to undo it all at once. Because remember, the chain rule says take derivative of the outside times derivative of the inside. So we're just undoing the derivative of the outside and the derivative of the inside in 2 separate spots. Some helpful hints for as you're trying to decide what u is. Again, these are not hard and fast. This comes with experience. Good places to start. If I have a power, choosing the inside of a power or radical, since radicals are powers also. Choosing the inside of a trig function. The exponent of an exponential, or the denominator of a rational. None of those are perfect. You will still have trial and error. Heck, I've been doing this for years. I still have trial and error. But those are good places to start. Things to check last. Saying u equals x, all it does is change the variable. It actually doesn't make anything easier. It just makes all the x's into u's. So that's incredibly rare that you would ever have that. Or having u equal the entire integrand. When that happens, you're probably going to have x's that show up when you solve for dx that won't cancel. So that is also incredibly rare. Again, notice I didn't say they're impossible. They're just rare. Of course, there are always exceptions to all of these, both the places to check last and even the good places to start. As you gain more experience with these, you will start to see the substitutions more easily. Because kind of the way it works is you'll be able to look at an integral and just, there's no chain rule or any complicated rule involved. It'll be kind of what we've been doing with antiderivatives. You just know, oh, antiderivative of x is 1/2 x squared. Oh, the antiderivative of cosine of x is sine of x. That's like 95% of the integrals you do. Then like 3% of the integrals there's chain rule involved. And that's where the substitution comes in. As you get experience, it gets easier.